Hi everyone, welcome to Chem 262, which is the second quarter of organic chemistry. And on this slide in the background, I have what's called a reaction map. So you can see that there are many different reactions that you can perform. And essentially, you're converting one functional group into another functional group. So for instance, maybe you want to convert a triple bond, an alkyne, into an alkane with just single bonds. Maybe you want to convert an alkyne into an alkyl halide. And sometimes these involve multiple steps to get from a reactant to a particular product. But that's what you can use these reaction maps for, is to figure out how can I go from one functional group to a desired functional group. And that's really what this quarter is all about. How do we go from point A to point B using different reagents? So before we start this week's topic, addition reactions, I do recommend reviewing energy diagrams, arrow pushing, carbocation rearrangements, and then nucleophiles and electrophiles. So that's all in chapter 6. Oops. And then I also just wanted to make a quick note. If you have the third edition of the Klein textbook, we are going to start at chapter 8 this quarter. If you have the second edition of the Klein textbook, you will start at chapter 9. So between the second and third editions of the textbook, initially substitution and elimination reactions were in separate chapters, but then in the third edition they combined those two chapters. So that's why the chapters are off by one. But if you ever get confused, just ask me, what chapter are we on? I can always guide you in the right direction. So I'm typically going to refer to the third edition of the Klein textbook. So I'm going to use those chapter numbers, but I'll try to also make it obvious what topic we're covering so you can, stay on track. All right. So let's actually review some of the topics from either chapter 7 or chapter 8, depending on which textbook you had. So let's talk about substitution reactions and elimination reactions. So we'll start with substitution reactions, and we'll just do a quick review. So remember, there are two types of substitution reactions, SN2 and SN1. Oh, I'm not sure why I wrote the 2 as a subscript. There we go. So remember the numbers in our substitution reactions here, those refer to the order of the reaction. So SN2 means we have a second order reaction. So if we write the rate law, that is equal to a rate constant K times the concentration of a substrate, which I'll just abbreviate sub, and that's multiplied by the concentration of the nucleophile, which I'll abbreviate NU. All right. So what that really tells us is that the substrate and the nucleophile react in the same step, or all in one step. So let's just draw a generic SN2 reaction. So let's say we have our substrate with a leaving group attached, and then we have our nucleophile. And remember, for SN2 reactions, the nucleophile should be unstable or very reactive. So it's typically going to have a negative charge. All right, so then remember that nucleophiles are electron rich, so they have electrons that they can donate. And the lone pair on the nucleophile will be attracted to anything that's positively charged or partially positively charged. And remember, the leaving group will typically be electronegative in some way, so it's going to draw electrons towards itself. So we end up with a partially positive carbon right next to the leaving group. So the nucleophile will be attracted to that partial positive charge, and that's going to kick out the leaving group, and the leaving group takes its shared electrons with it. So we end up with two new products. The first product now has the nucleophile attached to that partially positive carbon, and the leaving group took electrons with it, so it's now negatively charged. Okay, now SN1, the 1 tells us we have a first order reaction. So if we write the rate law, that's equal to a rate constant times the concentration of just the substrate. So what this tells us is that the rate determining step of this reaction only involves the substrate. And that's actually the first step of the reaction. So let's say we have a substrate with a leaving group, and we've got our nucleophile. And remember, for SN1 reactions, the nucleophile is weak or stable. It's kind of weird that we say it's weak and stable. Normally we would think strong and stable, but it's a weak nucleophile, which means it's stable and doesn't want to react as quickly as an unstable nucleophile. All right, so also in SN1 reactions, we need the leaving group to be a really good leaving group because it leaves first on its own. So we'll just write really good leaving group. All right, so first step, leaving group leaves, and we end up with an intermediate, which is a carbocation. And now this is where the nucleophile can come in and donate its electrons to the positively charged carbon. And at the end, we have our new products. So we have the nucleophile attached to that carbon in the middle. And then we have our leaving group, which is now negatively charged. Okay. Now let's also quickly review elimination reactions. Now, in an elimination reaction, we're essentially taking a molecule or a substrate that has all single bonds, and we're turning one of those bonds into a double bond. So essentially we're taking an alkane and turning it into an alkene. Now there are two types of elimination reactions, E2 and E1. And again, those numbers refer to the order of the reaction. So E2 is a second order reaction. So the rate is equal to a rate constant times the substrate, or the concentration of the substrate, and then we multiply that by the concentration of a base. So remember, in elimination reactions, we no longer have nucleophiles, we have bases, because remember, bases take protons, and that's what starts our elimination reaction. All right, so let's draw a hypothetical E2 reaction here. So we've got a substrate with a leaving group, and then we have a strong base or a very reactive base, so it has a negative charge. And remember that when we're performing an elimination reaction, again, the base is going to take a proton from one of the carbons. So that means we need to figure out where are the beta carbons, because remember, in elimination reactions, bases take hydrogens from beta carbons. So let's first find the alpha carbon, which will be right next to the leaving group. And then the beta carbons are next to the alpha carbon. So this substrate has two beta carbons, and they're the same. They're both methyl carbons. So we'll just arbitrarily pick the top carbon, draw some hydrogens here, and the base is going to take one of those protons. The shared electrons will be left behind to form a double bond, and then that's going to kick out the leaving group, which will take its shared electrons with it. So we end up with an alkene. We also end up with a conjugate acid, and our leaving group with a negative charge. So for E2, because it's a second order reaction, everything happens in one step. But for E1, we have a first order reaction. So the rate really only depends on the concentration of the substrate. So let's say we have our substrate with a leaving group, and it should also be a good leaving group there. And then we have a weak base, or a stable base. So similar to SN1, in the first step, the leaving group will leave all on its own. So we'll end up with a carbocation and our base. So again, the base is going to take a hydrogen from a beta carbon. So we need to figure out where the beta carbons are. So we have an alpha carbon in the middle where the leaving group was attached initially. And then we have three beta carbons because there are three carbons attached to the alpha carbon. Now all those beta carbons are the same. They're all methyl carbons. So I'll just pick the top one to show what happens. All right, so the base can now take one of those hydrogens. The shared electrons are left behind to form a double bond, and we end up with an alkene, a conjugate acid, which in this case will be positively charged, and then a leaving group. All right. Now, if you're feeling rusty on substitution and elimination reactions, definitely go back and review because this will kind of play a part as we move forward. We'll still be using substitution and elimination reactions from time to time, but also elimination reactions are important for understanding the next type of reaction, which is called an addition reaction. So this is our new material. All right. So in an addition reaction, we're essentially doing the opposite of an elimination reaction. So we said in an elimination reaction, we take an alkane, turn it into an alkene. Well, in an addition reaction, we take an alkene and we turn it into an alkane. So let's draw a hypothetical addition reaction. So we have an alkene, and then we have some sort of reagent. And later on, we'll talk about what this reagent could be, but for now, we'll just use an X and a Y. And in an addition reaction, the X and the Y are going to add across the double bond. So they're going to add themselves to those yellow highlighted carbons, which are called vinylic positions. So our product, we have those same 3 carbons, but we're breaking the double bond to form 2 new bonds, X and Y. Okay, so again, in an addition reaction, a reagent is going to add across that double bond, and we're breaking the pi bond to form our new sigma bonds. So we're breaking the double bond to form new single bonds. Now, in addition reactions, that pi bond, that double bond, is actually acting as a nucleophile. Now remember, nucleophiles are electron rich. They have electrons they can donate. And that's what's happening here. The double bond, or the pi bond, is breaking in order to form new bonds by donating its electrons. So in addition reactions, the pi bond acts as a nucleophile because it is electron rich. All right. So let's talk a little bit about the energy or the thermodynamics of addition reactions. So I'm going to redraw that reaction we just saw. And I'm actually going to draw my arrows a little differently here. You'll see why in a second. So we have a forward reaction and a reverse reaction. So the forward reaction we already said was an addition reaction. And if we go in the reverse direction, we're taking an alkane, turning it into an alkene. So that's our elimination reaction. So you could reverse an addition reaction or reverse an elimination reaction, whichever way you want to go. Now, one thing to remember, elimination reactions are favored at high temperature. So we tend to use heat, which we symbolize with a delta symbol. Now, the opposite process, the addition reaction, is favored at low temperatures or low heat. Now, let's talk about why that is. Why are addition reactions favored at low temperatures? Well, in order to talk about that, we need to look at our enthalpy, entropy, and Gibbs free energy. So let's write out the Gibbs free energy equation. So delta G, Gibbs free energy, is equal to delta H, enthalpy. And I'm going to write this a little differently, but I'm going to say that we add negative T delta S. And the reason I do this is just to separate the different components. So we have our enthalpy component, delta H, and then we have our entropy component, negative T delta S. So T stands for temperature, delta S is entropy, but we tend to clump them together there. Okay, so Let's focus on enthalpy to start. And remember, enthalpy can be calculated by taking the energy of the bonds broken and subtracting the energy of the bonds formed. So since we just have a generic equation up above, we can't really look up specific energies, but we can estimate whether delta H is positive or negative. So let's focus on the bonds that are broken in the reactants, and we'll highlight those in blue. So which bonds are breaking in the reactants of our addition reaction? Well, we're breaking a pi bond, and then we're also breaking the bond between X and Y. So again, we are breaking a pi bond and a sigma bond, a single bond. Okay, now let's look at our product and highlight the bonds that are formed. So which bonds are formed in the product? The one between carbon and X and carbon and Y. And those are both sigma bonds. Okay, so we broke a pi bond and a sigma bond, and then we formed two sigma bonds. So, which bond is more energy or is worth more energy? Is a sigma bond worth more energy, or is a pi bond worth more energy? Or another way to ask that is, which bond is stronger, a pi bond or a sigma bond? The sigma bonds. Sigma bonds are stronger than pi bonds. So if we try to kind of estimate how much energy is needed to break bonds versus form bonds, I would say that delta H of the broken bonds is less than delta H of the formed bonds, because we formed two stronger bonds, so those are worth more energy. Okay, so if delta H of the formed bonds is greater, and we're subtracting that, will delta H be positive or negative? Negative. All right. Now, if you need numbers to kind of think this through, let's say the energy of the bonds broken was 600 and the bonds formed was 800. So 600 minus 800 would give us like negative 200, right? So that's where we're getting the negative from, if that helps a little bit. Okay, what about entropy? Is entropy increasing or decreasing in this addition reaction? And remember, entropy is somewhat equivalent to disorder. So is disorder increasing or decreasing? It's decreasing, right? We have 2 moles of reactants and only 1 mole of product. So we're really increasing the order here. So things are becoming more ordered, less disordered. And when we have, or if disorder is decreasing, will delta S be positive or negative? Negative, because it's decreasing. All right, so let's kind of rewrite this on the next slide just to organize our thoughts here. So I'm just going to rewrite the Gibbs free energy equation. And then we said that delta H for an addition reaction is negative. We said that delta S is also negative. Oops. So if delta S is negative, what is negative T delta S? Positive, because a negative times a negative gives us a positive. All right, so in this situation, a spontaneous reaction would have a delta G value that is negative. So remember, if delta G is negative, that means the reaction is spontaneous. Now, in our delta G equation up above, when would delta G be negative? Well, that's going to depend on temperature. So, would delta G be negative at high temperatures or at low temperatures? Well, if the temperature is high or large, then that's going to make the positive part of our equation increase in magnitude, right? And so that's going to overpower the enthalpy part, the negative part. And that means that delta G will be positive. But if the temperature is low, then the positive part of our equation, that entropy part, is going to decrease in magnitude. It's going to be really small. So then the enthalpy part, the negative part of our equation, will increase. So that means that delta G is negative. So I hope that kind of makes sense how I stepped through that. But the main message here is that addition reactions occur or are favored at low temperatures. Oh, addition reactions So addition reactions are favored at low temperatures. All right, so hopefully this got your brain going, kind of remembering substitution, elimination, thermodynamics, and we just kind of sprinkled in this new concept of an addition reaction. So next time we'll talk more specifically about the different types of reagents that we can use in addition reactions. So what is that X and that Y? And what can we put there to make our desired products? So we'll talk about that in the next video. I will see you then.